Okay, in this video I would like to do a fairly involved integral in order to first of all demonstrate some of the types of integrals we'll be doing this quarter, but also to address one of the fundamental concerns a person might have about the Newton's law of universal gravitation. So, in fact, Isaac Newton invented calculus to answer this very question, which is Newton's law of universal gravitation consistent if we assume that it applies to point-like particles, or if we assume that it applies to a planet, a large extended object that is not point-like. So in order to address this question, I want to imagine that we have a planet like this, and we're going to calculate the force exerted by that planet on some small object. Okay, and I'll put the object over here. Okay, so the question is, if I split up that planet into a bunch of little point-like particles, you can imagine it's a bunch of little rocks, and I add up all the forces from every rock on that object, is the total gravitational force from the whole planet going to be the same as if the planet were concentrated into a point-like mass at its center? And I think that the answer is far from obvious. It's not clear whether that should be true or not, but we're going to find out whether it is by doing the calculation. Okay, so the first thing I'm going to do is imagine that I can treat this situation one spherical shell at a time. Okay, so this is not going to be the complete planet, but just some shell that we're going to treat as hollow. So you could imagine like a basketball or something that is just a thin surface on a sphere. And then at the end, we can add up all of the shells and get the effect of the total planet. That's actually kind of nice because in real planets we sort of expect to have some really dense stuff in the center and much less dense stuff at the surface. And so by splitting it up shell by shell, this is actually better than if we tried to do the whole solid sphere. Okay, I also want to consider just one ring at a time from this planet. Okay, so I'm going to imagine that I slice through this spherical shell, and I have just one ring. Okay, so we started out with a spherical shell, and then we consider just one ring. And again, we'll be able to integrate the effect of each ring in order to get the total effect of the whole shell. Okay. We will then also ultimately split up the ring into small little elements. So this small piece of the ring I'm going to call dm. So that's a small mass element of the whole planet. Okay, and so then by splitting the planet into spherical shells, splitting each shell into rings, and splitting each ring into a mass element, we have split up the planet into infinitesimal little pieces. Okay, so that's the setup for the problem. And what I want to do now is name some of the different distances in the problem. Okay, so the distance from the center of the planet to the object that we want to calculate the force on, I'm going to call r, and I'll use a capital R for this. I also want to name the radius of the planet, so I'll call that RE for the radius of the Earth, although this could apply to any spherical planet. And then finally, I want to name the distance from that mass element to the object, and I'll call that little r. Okay, so we have three different numbers here. Notice the two capital R's are both constants. So as we consider different mass elements around this shell, big R and RE are going to be constant that whole time. Little r will change. It will depend on which mass element we consider. Okay, I also want to consider the angles that are present in the problem. Okay, so there are a couple of angles that I'm going to need to name. So I'm going to name this angle theta, okay, the angle of the location of the mass element relative to this line that points to our object. And then I'm also going to name the angle over here alpha, okay, and that will end up being useful. Okay, so that's the setup for the problem. We have named a bunch of things, and you're going to find as you do more and more of these integrals that it'll become pretty clear that you'll need to name lots of extra things, and then we'll figure out the relationships between them. Okay, so now what do we do with this diagram that I made? Well, the first thing I want to do is use Newton's law of gravitation to figure out the force from that mass element. Okay, so from the mass element, we're going to have the small amount of force, which I'll call dF, because it's just a little bit of the force, and then we'll integrate to get the total force, is going to be equal to G times the mass of the object, which I'm going to call m, and then dm, which is the mass of that element, over r squared. And r is that distance from, again, the object to that little mass element. Okay, so that's just Newton's law of universal gravitation. If we want to figure out the total gravitational force from the entire ring, well, it turns out that there will be some cancellation because the direction of the force on the object is going to be towards the mass element. But we know that once we add up the whole planet, it'll have to be directly towards the center of the planet by symmetry. If it were in some other direction, that wouldn't really make sense. So what I want to do is I want to figure out just the component of this force that is to the left, okay, the x component of the force. So dfx is going to be the same magnitude, gm dm over r squared, but times just the component that is in the horizontal direction. Okay, so because the force is going to lie along this line that I named little r, we're going to need a cosine of alpha in order to select out just the component that's along big R. Okay, so that's going to give us the force from that one mass element that is in the correct direction. But then if we consider the situation, every element along the ring is going to contribute that exact same amount of force. It doesn't matter which part we look at, the x component is always going to be the same. There might be different y and z components, but once we add up the whole ring, those are going to cancel out, and all that will be left is just the x component. Okay, so now what I'm going to do is I'm going to say for the ring, dfx is equal to g m d, and I'll call this big M to indicate that it's not quite the same as the other one, over r squared cosine alpha, where d capital M is now the mass of the whole ring. Okay. All right. So now we've got a pretty good start for this. Now, what we're going to need to do in order to integrate over the entire spherical shell is we're going to have to get rid of some of our variables. Because at the moment we have an alpha and we have little r, and both of those are going to be different for each ring that we calculate. So we have to get it down to one integration variable, and then we will be able to integrate to get the effect of the entire spherical shell. Okay, so in order to do that, what I want to do is consider the density of the shell, because if I know the area of that ring, then I can use that area to figure out the mass of the ring. Smaller rings ones that are close, like near the close end of the planet or the far end of the planet, are going to be smaller, and ones more that go around a whole equator of the planet or a longitude of the planet, those are going to be larger. Okay, so I need to consider the density of the planet. Okay, so what I'm going to do then is I'm going to call the density d capital M over dv, and I'm going to call that rho. So rho is a pretty common variable for us to use for density, so that's what I'm going to do. Okay, and so dm then, just doing some rearranging, is rho dv. Okay, so the more volume one of these rings takes up, the more mass it will have. Okay, but that's not the whole story. So what I really want to do is I want to relate dv to the area of that ring. Okay, so what I can do then is I can say rho times the area of the ring times whatever the thickness is. So I'll call the area of the ring dA and the thickness t. And then at the end we'll be able to cancel that out. So the thickness won't end up actually mattering at the end of the day. Okay. So how do I figure out the area of a ring that is on a spherical shell? Well, there are a couple of approaches you could take to this, and there's sort of the harder way, which is more precise, and then there's sort of the physics shortcut that I'm going to advocate for. So what I want you to imagine is that, say you took something like a basketball where you have this thin spherical shell, and you sliced out this ring that is illustrated in my diagram. Well, if you made one cut somewhere on the ring and you tried to lay that out flat, it wouldn't look very much like a rectangle. But if you imagine that it's kind of rubbery, then you could distort it only a little bit and get it into a shape that's very close to a rectangle. So we've got this shape that's very long and skinny, and my claim is that we can basically take the length of it times the width of it, and that will give us the area. Okay, so dA is going to be approximately the length times the width for that rectangle that you get by taking the ring, cutting it, and kind of stretching it until it looks like it's a rectangle shape, just distorting it. Okay, so the length of that is going to just be the circumference. So that will be 2 pi times the radius of that ring, which we can figure out in a moment. And then the width is going to be RE times d theta. Okay, so what is d theta? Well, theta is illustrated here, and d theta is basically the angle that is taken up by the ring. Okay, so let me kind of sketch in d theta. Theta goes from there kind of to there. So that angle here is d theta. You imagine making theta ever so slightly larger to go from one end of the ring to the other end of the ring, and then you have d theta. Okay, so you should take a minute to convince yourself that the width of that ring is RE times d theta, and that 2 pi times the radius of the ring is the length. Okay. Well, in order to get the radius of the ring, what I'm going to do is use theta. So the radius of the ring is going to be RE times sine theta. Okay, and then the other part, RE times d theta, that has stayed the same. Okay. So if I rearrange this slightly, I have RE's in two places. I have a 2 pi and a sine theta d theta. So 2 pi RE squared sine theta d theta. Okay, that is dA for the for that ring, the area of the ring. Okay, and then I'm going to plug that into my dm expression. So dm is equal to rho times t times dA, which is 2 pi re squared sine theta d theta. Okay? So now I'm going to plug that into my expression for the force from the ring that I had a moment ago. Okay, so for the ring, we have dfx is equal to gm over r squared cosine alpha, and then dm was rho t times 2 pi re squared sine theta d theta. Okay, so that's a lot of things in that expression. But we've got it in terms of all things that we know. So we know information about the angles, alpha and theta, and we know information about little r. And so what we need to do then is come up with ways to eliminate some of those variables and get it down to just one integration variable. Okay, so at the moment, we have r, theta, and alpha, and we need to get rid of 2 of those. Now, in principle, you could get rid of any 2 at all that you want. There's no real reason why it would have to be in terms of r or theta or alpha. But what we're going to end up doing is getting the whole expression in terms of r's, and we're going to eliminate theta and alpha. Okay, so how do we do that? Well, looking back at the picture here, we can see that alpha and theta are related to each other. Those are not totally independent. Okay, so what I want to do is relate the length of this line, where I have this line be perpendicular here, using the 2 different angles. Okay, so if I take this line that's along big R, I can express it in terms of alpha because little r times cosine of alpha is going to be equal to that length. Okay, so that's just using trigonometry. But I can also express that line in terms of theta. So if I express it in terms of theta, well, re times cosine theta is going to be the length, this length, along that line. And so r minus that length will be the same as r cosine theta. Okay, so r minus re cosine theta. Okay, so now I have a relationship between alpha and theta. So I'll be able to eliminate one of those variables using that relationship. Okay, so what I'm going to do is I'll copy this down to where we can use it. Down here. And notice that we actually have cosine alpha in this expression. So what I'm going to do is I'm going to rewrite this and take cosine alpha and replace it with that expression that I just found. So dfx is equal to g m over r squared times, well, cosine alpha is that expression divided by r, so r minus re cosine theta over r times everything else. So rho t times 2 pi re sine theta d theta. There's a square over here. Okay, so what I have now is an expression that's in terms of just theta and little r. Okay, so what I would like to do then is come up with a relationship between r and theta. Okay, so if I go back up to the diagram, r and theta are not independent of each other. If I imagine making theta bigger, then r becomes bigger as well. So there's a relationship there. Well, there's more than one way to connect those quantities, but what I'm going to do is I'm going to use the law of cosines, which you may be a little rusty on, but that's okay, don't worry about that. What the law of cosines says for that blue triangle is that r squared equals big R squared plus RE squared. So far that looks a lot like the Pythagorean theorem, and that would be it if theta was 90 degrees, but it's not. So we need to include minus 2r RE cosine theta. Okay, so that's a relationship that relates little r and theta to each other. And notice those big R's are all constants, and so they're not going to make this expression much more complicated than it would be without them. Okay, so if I take this and move it down to where we want it, bring this over here. Okay, what I want to do now is I'm going to want to write this in a form where I can replace the cosine theta with something in terms of r, and then also replace the sine theta. Okay, so I'm going to do the cosine theta first, since I already have a cosine theta. So what I'll do is I'll just simply solve this. So r squared minus capital R squared minus RE squared equals minus 2r RE cosine theta. Okay, and in fact I have RE cosine theta, so I'll just leave that there, and I'll divide both sides by negative 2r. So I get r squared minus big R squared minus RE squared over negative 2r equals RE cosine theta. Okay, so now I can replace cosine theta. What do I do about the sine theta, though? That's a little trickier. So I could try to use the relationship between sines and cosines, which actually turns out to be not that helpful in this case. But what I'm going to do instead is I'm actually just going to take the derivative of this expression, because that will turn the cosine into a sine. So that is going to be a pretty convenient thing to do. All right, so I have to decide if I want to take the derivative of both sides with respect to r or with respect to theta. I have to pick. I can't do something different to each side, so it has to be the same derivative on each side. So I'll take the derivative of both sides with respect to theta. So when I do that, on the left-hand side, I'll get 2r, and then from the chain rule, dr d theta. Okay, and then on the right-hand side, well, the derivative of a constant is 0, so those first two terms go away, and I'm going to get 2r RE sine theta. Okay, where did the minus sign go? Well, when I take the derivative of cosine, I get negative sine, and I already had a negative, so those cancel out. Okay, so that's fine, but now I have this dr d theta. What do I do with that? Well, it turns out that's okay, because actually I had a d theta already, and I wanted a dr instead, because I want to integrate with respect to r. So what I'm going to do is I'm actually just going to split that derivative. So I'm going to have, also at the same time canceling out the r's, I'll have r dr on the left, and then r RE sine theta d theta on the right. Okay, and then that actually works out really nicely because I have sine theta d theta, which is exactly what I wanted. Okay, so now I'm going to take my expression for the force from the ring. So dFx equals gm over r cubed, because I had an r squared and an r on the bottom, so I'll just combine those. And then in parentheses, r minus RE cosine theta, but I have an expression for that. So I'll put in little r squared minus big R squared minus RE squared over negative 2r. Okay, so those minus signs will cancel out. And then rho times t times 2 pi. And then to replace the sine theta, well, I've got REs. I'll keep those REs as they were. And then sine theta d theta is going to be r dr over r re, like this. Okay, so now using a variety of algebraic techniques, I was able to get everything in terms of constants and the one variable lowercase r. Okay, so what I want to do is, before going much further, I want to clean this up a little bit. So I'm going to move all the constants over that I can. So this will be g times m, and then I'm going to have to keep the stuff in parentheses together. But rho t 2 pi re squared over r times re. Okay. Then I have the stuff in parentheses, so r minus r squared minus capital R squared minus re squared over, and I'm actually going to take that minus sign and combine it with that one to make this a plus, and have 2r on the bottom. Okay. And then I'm left with an r dr on top and r cubed on the bottom, so I'll just have dr over r squared. Okay, so that's a little bit cleaner than what I had a moment ago. Okay, so now we just need to integrate. Okay, so the total force in the x direction will be the integral of the force from each ring, which will be the integral of all these constants, so g m rho t times 2 pi. I have an re on top and on the bottom, so I'll cancel one of those. So I just have re on top and an r on bottom. And then I'm going to actually distribute the r squared. Actually, let me take one more step before doing that. I'm going to combine the terms that are inside the parentheses. So this will be 2r squared plus little r squared minus big R squared minus re squared over 2r, and then dr over little r squared. Okay. And then I can actually do a little more algebra before actually doing the calculation. So let me bring the constants out front. Gm rho t 2 pi re over 2r squared. And then the integral, well, I have actually 2 capital R squared minus r squared, so I can combine those. So r squared plus little r squared minus re squared over little r squared dr. Okay, and at this point we should really figure out what the limits of integration are, because this is in fact going to be a definite integral. Okay, so what is the smallest value of little r and what is the biggest value of little r? Well, the smallest little r can be is the point on the planet that's closest to the object, so that will be big R minus the radius of the planet. Okay, and then the furthest it can be is the far point on the planet, so big R plus RE. So those will be the limits of integration. You should take a moment to look at the diagram and decide that that makes sense. Okay, so the limits of integration are going to be from big R minus RE to big R plus RE. Okay. All right, so now we can actually do the integral. Okay, so what I'm going to do is I'll copy these constants again, gm rho t times 2 pi re over 2r squared. And then I've got little r squared over little r squared, so I should probably fix that up. So little r squared over little r squared is going to be 1 plus r squared minus re squared over little r squared dr. Okay, and again we're evaluating from r minus re to r plus re. Okay, so now when we do it, we're going to get gm rho t times 2 pi re over 2r squared. Okay, and then integrating 1 is going to just give me r. Integrating 1 over r squared will give me minus 1 over r. With the same limits. Okay, so when we then plug in those numbers to get a final result, when I integrate gm rho t times 2 pi re over 2r squared. So integrating r from r minus re to r plus re, well, if I plug those in, then I'm going to have the r's cancel, and I'll get 2re. Okay, so that's what I get for that part. Interestingly, for the second term, when I plug in r plus re and r minus re, this actually is going to factor because we have a difference of squares here. So this is going to end up being r plus, r minus re when I plug in r plus re on the bottom, and then minus r plus re when I plug that in on the top. Okay, so what I end up with that in that case is re, or r minus r cancels, negative re minus negative re, those add together, and then I have that minus sign. So everything in the square brackets is going to become g m rho t 2 pi re over 2r squared, and this just becomes 4re. Unbelievably enough. So what do we do from here? Well, I'm going to clean this up a little bit and lump some things together. So I'm going to keep g, m, rho, and t. Notice I have a 2 on the top and on the bottom, so those cancel, but I still have this 4 left over. So I'm going to have 4 pi re squared, which I want to lump together, and then over big R squared. Okay, so what's 4 pi re squared? Well, that's simply the surface area of the planet. So the surface of a sphere is 4 pi r squared. That's exactly what appears here. If I multiply that by the thickness, then that is going to give me the volume of the shell. Okay, so this is g m rho times the volume of the shell over r squared. And the density times the volume is just the mass of the shell. So g m times the mass of the shell over r squared, which is exactly what we would expect from Newton's law of universal gravitation. We can treat that spherical shell as though it were a point mass concentrated at the center of that shell. Okay, so there are a lot of things to take away from this, but I will save that for another video.